realized that I was so excited to start that to tell you who I am. I guess most of you know me, but yeah, I'm Adi. I am quite a long time contributor and head of RIOT. And next, we have members in the community and also the maintainer, Carl, who was bachelor students, important new a lot of ADI. We heard of already in the international unicoap. Yeah, and will present to you with his proposal for how to do CoAP environment.
Okay. Good afternoon, everybody. My name is Carl, and I'm going to talk about unicoap, which is the new unified and modular CoAP suite in RIOT. Before we start, I'd like to dive a bit down on why we need a new CoAP library. If you think about CoAP, the first thing that probably comes to your mind is the different transport, the constrained application protocol supports, such as UDP, the DTLS transport. Legacy deployments can also use TCP and TLS. And there's also an active internet draft by Christian for using unicoap over Bluetooth Low Energy, or GAP to be more specific. And so the first problem that arises is that the messaging and the PDU format differs. And the other thing is, if you think about CoAP, is there are a lot of extensions like blockwise transfer, resource observation, and stuff like that. And these features influence each other or build on top of each other. And this makes things a lot more complicated than, yeah. So what we need is an API that can handle this complexity, and a library that is that guarantees an application can be agnostic towards the transfer that's used underneath. And developing such a library isn't as trivial as you think, because I mean, separating something in layers, as I've done it with unicoap, is not that easy because there's a certain cost associated with it, and you have to manage state across layers, and modularization itself, due to enclosing features and different kind of areas of the stack, can also have an impact, especially in a constrained environment. Yeah, and of course, as you already know, unicoap is implemented in RIOT. So before we move any further, let's have a look at existing CoAP libraries in RIOT. We've got nanocoap SOC and gcoap, both of which use the nanocoap parser, which is a bit inconvenient. If you remember, you have to insert CoAP options in the order specified by the RFC, which isn't that easy to deal with. You also have to insert options before you append the payload. So if you want to implement something like blockwise transfers on a lower level, the payload, like the message is already has already been built, so you can't really do anything with the options anymore. They don't feature any transport abstraction. They don't only support UDP and DTLS. The APIs are either synchronous or asynchronous. Like OSCORE isn't implemented, could be implemented, but it's not obvious how that could be done. Resource observation support by both of them. They only support blockwise transfers using helper structures, which require manual intervention from the application. And what we want is, of course, all of that, and in the case of OSCORE, at least some way of integrating OSCORE in the future. So yeah, let's talk about unicoap. I'm going to start with the design of unicoap. At the bottom, we have the transport layer in unicoap. This is basically what the transport layer comprises is the operating system networking APIs. And then there's a small glue layer between like the socket API. I mean, it doesn't have to be the socket API, but it can be the socket API. Any networking API is fine. Between set operating system level transport API and unicoap. And above that, we have the different messaging and transport implementations of CoAP. Think about RFC 7252, which is CoAP over UDP and DTLS. You've got confirmable messages, non-confirmable messages, this entire reliability mechanism where you retransmit messages until you get an acknowledgement, and only then you stop retransmitting. And this works using an exponential backoff. And this mechanism is actually split between reliable transports and unreliable transports. And I mean, CoAP over Bluetooth uses even another kind of messaging implementation, which is similar to 7252, but not the same. So these implementations also differ. And with that, of course, the PU format. And above that, we've got a common request and response layer. This is actually that makes CoAP so unique, that you have a common ground, regardless of what transport or messaging implementations you use. And this request response layer is again leveraged by advanced features such as blockwise transfer and observe. And on top of that, of course, sits the application. Now in unicoap, we group support for a given transport, which consists of a messaging implementation. So think of this retransmission or reliability mechanism for CoAP over UDP in combination with a transport. And we group that support into a module, which we call a driver. So the CoAP over UDP driver is a module that's comprised of both the messaging implementation and the transport implementation. So there's basically an interdependence inside the driver module. Let's look at how these layers communicate with each other. Let's imagine there being a client application that does want to send a large request. And what unicoap, or I mean, the exchange layer, what the exchange layer would do is it would split the request in separate messages and send them and forward them to the driver. And the exchange layer would manage this process of continuing a blockwise transfer, i.e. Receiving a response, sending the next block until the last block has come in. So the application can completely agnostic regarding there being a blockwise transfer in progress. And the messaging or the driver usually works this way. You've got the messaging and framing layer, and then all the retransmission reliability stuff that's going on between the messaging and transport layer is handled by the driver. A quick round of terminology. I'm calling like the effort of trying to send a message a transmission. Transmission always happens in the driver, and the effort to send a message on the exchange layer, i.e. using like this REST model, an exchange. Okay, now let's look at how you could use this client API in unicoap. So down here in the main function, you see we craft, oh, actually you don't see anything. Okay, you see a request message that's being crafted with the request method of get, and then we specify destination where that message should be sent to. And this is where like unicoap abstracts the kind of endpoint you want to send your message to. We do not only allow URIs to be passed to unicoap, we also allow endpoints, and this abstraction is encapsulated in this endpoint. Destination, sorry, not endpoint. So if we look at the destination is basically tagged union that can represent either an endpoint or a URI. And the endpoint in turn can also be like the endpoint that's connected to a different transport. So the endpoint can both be UDP transport, but it could also be a GATT MAC address if said internet draft would come into effect. Right, and this abstraction is built into this destination structure. And URI support is also modularized. So you could basically leave out URI support if you don't need it. We also support synchronous and asynchronous requests using like the regular event queue. We abstract the reliability mechanism that's used by CoAP over UDP and stuff using flags. You can supply when initiating a request. For example, the reliability flag implies unicoap needing to use confirmable messages if UDP or DTLS are used. You could also say, well, use blockwise transfers, automatically reassemble the response using the reassemble flag. And support for these blockwise transfers is also modularized in a separate module, which we call unicoap blockwise. And then once you've gotten the response, you can just handle it and completely ignore which transport you received that message over. Moving on to the server, the server is quite similar to GCoAP in terms of how you define resources. You can use the regular cross-file arrays, which are hidden behind this unicoap resource macro you see at the top. Okay, so you don't see any highlighting, but I'm focusing on the upper part right now. You specify path, what method to use, and I should say what methods you want to allow for the given resource. We don't have like a series of custom flags for resource definition. You can use the regular methods you would also use when constructing a new message in the client API. We do that with a custom macro. We could also, like, if there happens to be a use case when your application can or should only be reached over encrypted transports, for example, you could restrict the set of protocols you want your resource to be reached over. And these transports are again modularized into different modules. And if you do want to use confirmable messages for the response, you can tell unicoap to do so. And we also optionally support deduplication, which is a pull request that will come later on, where like duplicate message received over unreliable transports are filtered out. And so if the resource is doing something very expensive, which may be a niche use case, I know, then you can use that feature. And once you've gotten the request, you can just respond to using predefined methods. There will also be a pull request that supports deferred responses, which will be useful if you develop a server application that basically initiates another request and you want to respond after the request handler has already returned. And what this would help you do is to prevent blocking the event loop, which processes incoming requests. So if you think about a proxy that needs to wait for the response from the other server to come in, you could use this deferred response feature to not block any processing. Okay, let's look at what all these niceties cost us. We used an NOF featherboard and GNSC and IPv6 over local wireless networks and 15.4 and turned on all sorts of optimization. Let's look at the size and flash. You see the three different stacks, unicoap, gcoap, nanocoap, SOC. The yellow or brownish colors signify the core components of the stack. You see that unicoap separates core functionality and the RFC 7252, which is the UDP stuff, or like reliability mechanism with the exponential backoff, because we can, and it's really hard to separate this kind of functionality in gcoap because there's no layer separation. So it's not really that easy to measure that. We see unicoap has got a slightly higher flash consumption. The UDP and DTLS consumption is really the same. Again, not really measurable in nanocoap because there's no layer separation. Like the advanced features do consume memory in terms of flash, but it's manageable. It's not really that high compared to like the DTLS includes the entire tiny DTLS implementation, by the way. So I think this is manageable. Looking at memory sizes, unicoap and nanocoap SOC support using an optional thread that runs in the background. You don't have to. You can also use unicoap on your own thread and run the processing loop there. gcoap only supports like a fixed background thread. Memory required for core state management is roughly the same, which is actually not really that surprising considering that is the same kind of data, and the only difference is how it's represented in memory. UDP and TTLS is quite the same. Blockwise transfers, yes, requires memory, but do note though that this size is configurable. In this example, we use two 512 byte sized buffers for reassembling responses. So this is, you can set the number of parallel blockwise transfers you want to allow and the size of the buffers used in them. So modularization helps us reduce the memory footprint, and layering doesn't really have anything to say in the equation. Looking at stack usage and the features, the advanced features, we see roughly the same memory usage as in gcoap. This is the peak stack usage, except for server applications where you see the dotted part. this requires a little more stack memory, and the reason for that is actually quite easy to explain if you think about it, like a message that has to travel from below the stack to the application on top of the stack. And for client applications, the journey of the message ends there. The function just returns and the stack gets deallocated. But for server applications, you have to call a send response method, which basically delegates the message back down to the stack. So if you've got a higher memory consumption because of that back travel to the bottom of the stack. Yeah, it's roughly 250 bytes. As the last thing, I want to look at traversal times. So we measure the time it takes for a message to go from the bottom to the stack to the top and then back down when the application has responded. And times for unicoap and gcoap are actually quite similar. And like the largest influence is the messaging implementation itself, which you can see here. And the other parts of the stack aren't really that relevant compared to the time required to send the message. Yeah. So what we have is a modular CoAP suite for RIOT. We've got a flexible transport API. We can support advanced features. The API is designed in a way that reduces boilerplate. And we can unify the existing 3 CoAP or partial CoAP implementations in RIOT. What remains to be done is also support for other drivers, and of course the existing applications such as like the virtual file system and DNS server CoAP that still need to be adapted to the new module. So with that, I'd like to thank you, and yeah, please help me review all this stuff. Yeah, I'm done.
Questions? Thank you so much for the presentation. I see that this is unifying, basically, CoAP and unicoap. What happens also for stacks that implement their own CoAP implementation? For example, OpenThread, and I think also OpenWSL, also provide a CoAP implementation. Would it be possible also to use the same unicoap CoAP handlers? You have to base the same API to the user, so basically, the application can use the same.
Yeah, I mean, first of all, the design is universal, so you could implement something similar, but you could also use the same implementation. The only thing you would have to modify is like the glue layer between the operating system level transport API, of course, but that would be different. But the API on top isn't really dependent, right? Of course, you've got something like the event queue, which you would need to find a replacement for. But other than that, there's nothing really that ties it to RIOT in a way that would prevent you from extracting it. But of course, it works best in RIOT.
Any more questions?
Not a question, but just a very, very big thank you. I would have loved to have done this myself, and I never got around to it. That you did it. Thanks a lot.
Yeah, thank you.